Yeah. So today is lecture 4 of physical metallurgy. So lecture 4. So today we'll concentrate on the iron carbon diagram. So basically we'll talk about two things: steel and to some extent cast iron. So that'll be the topic of the day. And the iron carbon diagram is probably the most important phase diagram in metallurgy, not only because of the tonnage of steel used, but iron carbon diagram has reactions which cover a gambit, so many different metallurgical reactions. So it's a good diagram to understand. So for metallurgists, this is probably the most important diagram. So the vertical axis is temperature, always in centigrade, and the horizontal axis is percent carbon, always by weight. So in metallurgy, we don't deal with molar percent, we always deal with weight percent. Okay, so from the top, steel, actually pure iron, melts at 1538 degrees. That's the melting point of pure iron. And the first reaction is what we call the peritectic reaction. So let's talk about, so this is peritectic reaction. And in these lectures we have not covered peritectic reaction, so this is something new. So here we have liquid, which is above the melting point of iron. And suppose I come down at this composition. So this composition is 0.17% carbon. This composition is 100% Fe. So if I move a little bit to this side, I get to 1.7% carbon. That's this, what we call peritectic point. So this is an invariant point. Are we assuming pressure is constant? If you change pressure, this point temperature and composition will change, but in metallurgy, we are mostly working on 1 atmosphere pressure, so pressure is constant. So this temperature is 1495 degrees, and this point is 0.17% carbon. This one is 0.53% carbon, and this one is 0.09% carbon. So let's suppose we take this alloy, which is molten, and we cool down this way. So slowly we're cooling it. I emphasize the word slowly because slow cooling, very, very slow cooling, because this is an equilibrium diagram. Things get really complicated if you were to cool this fast. So for today's lecture, everything is slow cooling. We try to stay as close to equilibrium as possible. So at this point, you have liquid plus a phase called delta. So when you cool below that point, you have more delta and less liquid. So when you get to the peritectic point, so let's get to the peritectic point. So what I've done is I've started cooling from here, and I get down to this 1495 degrees centigrade. So at that point, like we can ask, how much liquid do we have? So we're just above this temperature. So let's say +1 degree. So if we are above this line, so at that point, how much liquid do we have? How much delta do we have? We can say that the percent of delta by the phase rule will be 0.53 minus 0.09, 0.53 minus 0.09, and the numerator will be 0.53 minus 0.17. So that'll be the percent of delta. And the percent of liquid will be the same denominator, and the numerator is 0.17 minus 0.09%. So this is what we call the phase rule. No, this is called the level rule. So with this rule, at any point of the phase diagram, you can calculate what is the amount of the two phases. Okay, so once we get to this point, just below that point, you have a phase called gamma. Gamma is also called austenite. Austenite is a very important phase in metallurgy, in steel. So this peritectic reaction, what the peritectic reaction is delta plus liquid gives you gamma. And gamma is austenite. So that's the peritectic reaction. Now, suppose your composition is over here, which is hypoperitectic. So if I can move over here, hypoperitectic composition. So here what happens is, when you get to this point, let's say just above this line, which is, let's say, 1496 degrees centigrade, you have, again, you still have delta plus liquid, but you have more delta than the peritectic, right? So this reaction will give you delta plus gamma. So you're in this box. So that box has delta plus gamma. And if you were over here, which is called hyperperitectic, you would have your delta plus liquid giving you liquid plus gamma. This area is liquid plus gamma. So that's the peritectic reaction in a nutshell. Now, peritectic reaction, this whole reaction is at almost 1500 degrees centigrade. So it really doesn't have much effect at lower temperatures. So let me just fill up more of this diagram. So this comes down like this comes down like that, and here we have another reaction, and I stop at this point here, and this is 6.7% carbon. So let me just complete this diagram. Okay, this is 2.1%, this is 0.77%, this temperature is 727 degrees, this one is 1148 degrees, this composition is 4.3%. So this is the complete, actually not complete, but this is as complete a phase diagram as we want for the iron carbon diagram, because beyond 6.7%, that composition is useless for us. We don't really care what happens beyond 6.7%. At this point, this stoichiometrically, this is Fe3C, and we call this this intermetallic phase cementite. So Fe3C intermetallic is called cementite, and this we have austenite phase here. So this would be liquid plus austenite. So this is liquid plus austenite. This is liquid. This is liquid plus Fe3C, and this whole region is gamma plus Fe3C. And okay, so let me not get too far ahead. So at this point, we can ask ourselves, what is steel? So what is steel? So if you had asked a question to somebody, let's say in year 1900, they would have been totally clueless. They don't know what steel is in 1900. But they were using steel, but they had no idea what steel is. So steel is an alloy of iron and carbon with carbon less than 2.1%. So when carbon is less than 2.1%, that is steel. So what is cast iron? So cast iron is, you guess the answer, is when the carbon is more than 2.1%. That's cast iron. Now steel can be just iron and carbon, but cast iron cannot be just iron plus carbon. It also needs silicon. So you can't have cast iron without silicon, because silicon, what it does is it stabilizes graphite. So you might ask yourself, if I have an alloy of iron and carbon, why don't we form graphite? The answer is you can, but you have to add a graphite stabilizer. So silicon is a graphite stabilizer. So now this is more of a ternary alloy, right? But for all practical purposes, you can use this phase diagram or a modification of this diagram to deal with the iron, with the cast iron. So the first bridge ever built out of iron carbon alloy was, I think, in 1791. Let me check that date. I think it was 1791. And, not degrees, 1791 year. In England, in UK, they built this first cast iron bridge. Why didn't they build a steel bridge? Why a cast iron bridge? Back then, they couldn't build a steel bridge because notice that steel melting is much higher than cast iron. Cast iron is beyond 2.1%. So the cast iron melting point is low. So you could cast the bridge members in a factory and bring them to the site and bolt them together by using cast iron. But the 1791 was too early to be able to make steel and pour it and cast it, because it takes very high temperature. So to get back to the diagram, I mentioned this peritectic point is an invariant point. We have two other invariant points. This one over here, and this one we call the eutectoid. So this is a new term. And this one over here, we have already studied, and this is eutectic. So eutectic has a liquid phase above the eutectic point. Eutectoid has a solid phase. So this is solid. So here, a solid is going to solid. Over here, liquid is going to solid. So that's eutectic. So we have three invariant points in this phase diagram. So we mentioned that steel is from 0 to 2.1% carbon. That's steel. But actually, most steel is in a much narrower range. So most steel is about, let's see, so this is a 0.77. So most steel is from here to there in this range, from 0.2 to 0.3% carbon. So this is where most steel resides in composition. Now, if you're making a knife, then of course it's a little different, because you can make a knife or some springs from 1% carbon steel. But beyond 1%, so in this range, there is not much use of this composition. So that's because, as we'll see, the amount of carbide increases too high, so steel becomes brittle. So typically, the steel ranges from 0.2 to 0.3%. Most structural steel is in that range. And what other difference do we have between steel and cast iron? So steel has two phases. Okay, before I go there, let me discuss this eutectoid reaction. Or I can do that a little later, sorry. So over here, I have gamma plus alpha. Over here, we have gamma plus ferrite, and over here we have alpha plus cementite. So the eutectoid reaction is where austenite goes to alpha plus Fe3C, the cementite, and so steel contains alpha plus cementite. Those are the two phases in steel. In cast iron, you can have alpha plus cementite plus graphite. So you have an extra phase, which is graphite. So that's some of the differences between steel and cast iron. Okay. So just to reemphasize, we are only dealing with a very partial phase diagram for iron and carbon, and we only go up to 6.7% carbon. And I just want to also say this is equilibrium phase diagram. And since we are talking about steel today, we'll concentrate in this region, in this composition region, actually, right over here. So we'll spend, from today's lecture, we'll spend time on this eutectoid reaction. Because this eutectic reaction is for cast iron. We're not interested in this today. Today we are interested in the eutectoid reaction. And we are dealing with equilibrium phase transformation, which means very slow cooling. So the emphasis is on slow cooling. Okay, let me just clean up this area a little bit. Maybe I can redraw it because I want to spend more time on this. So this point is 0.77% carbon. This temperature is 727, and this temperature, let me see what that is. That's 912. This is 912 degrees. One other reading I want is this composition is 0.22% carbon. So let's discuss this eutectic reaction. So I'll be using a term called pro-eutectoid transformation. Of austenite. So what that means is, this is the eutectoid line. So pro-eutectoid means before eutectoid. So we're cooling down from the molten state. We get to so when you get down to this temperature, we're in austenite region, austenite phase all along, throughout austenite. So at this point, we start transforming the austenite, and we'll end up with alpha plus cementite. So above this point is pro-eutectoid, because this is the eutectoid reaction, right? So what happens is, if the carbon is, let's say, at this composition where the carbon is less than 0.77%, that is called, so what do we get over here? We will have the gamma transforming to alpha plus gamma. In other words, so this is alpha here, this is alpha plus gamma. So in this reaction, we have alpha plus gamma, and if we have carbon equal to 0.77%, then the gamma transforms directly to alpha plus Fe3C. That's the eutectoid point. If we are above the eutectoid, meaning carbon is more than 0.77%, then the gamma goes to gamma plus Fe3C. So depending on where you are in composition, you get different pro-eutectoid transformations. Now, of course, this transformation is eutectoid transformation. So in a way, it's not pro, right? At this point is where the transformation actually happens, whereas above this point, we have pro-eutectoid transformations. So let's take this case over here. We have, let me draw the structure. So the grain structure for, I'm just drawing a few grains for austenite. So let's suppose we are in the austenite region. It's a single phase, and this is austenite. Now if you were to come to this temperature, just at this boundary, below that, I'll get alpha precipitating out. So that alpha will precipitate out along the grain boundaries. So alpha will precipitate at the grain boundaries. So, I mean, not exactly the way I've drawn it. We'll discuss this in more detail in a few minutes. So alpha will precipitate at the gamma grain boundaries. So why not in the middle like that? This is energetically not possible. Just like when you have a soda bottle, the gases created in the soda bottle, they're not inside the liquid, they're at the surface of the glass. Because inside the liquid, that vapor that forms has to have infinite pressure to form the vapor, that bubble, because pressure is inversely proportional to radius of the bubble. So that's for gas bubble formation. So bubble has to be 0 to begin with, right? So pressure to form the bubble is infinite. So that's why bubbles do not form homogeneously within the liquid. They form on surfaces where it's more energetic to form that bubble. Similarly over here, the alpha will not form here, it'll form on the grain boundaries. And we'll discuss that in some detail soon. Similarly, so this is alpha. Similarly, the Fe3C will also form on grain boundaries. But what if you were doing something different? So right now we're cooling from liquid state down, but sometimes you heat treat the metal. So most steel heat treatment involves taking steel at room temperature, heating it in the austenite region. So notice, to go from room temperature, which is alpha plus Fe3C, to austenite, you have to dissolve the Fe3C so that you get a homogeneous austenite, right? So basically alpha and Fe3C have to react and disappear and give you austenite. But if you don't hold here long enough, then you could have Fe3C particles inside the austenite. So then you can have precipitation on these particles. So as a rule of thumb, in metallurgy, if you're given a rod of steel, let's say 1 inch in diameter, right? And you're asked to austenitize this steel, meaning you want to make it homogeneous to austenite. For 1 hour of, for 1 inch diameter, you need to hold for 1 hour. So that's typical rule of thumb. If it's 2 inches, 2 hours, etc. So that's the amount of time you need to make the steel homogeneously austenite. Okay. So with that, let's discuss, go back, and we'll talk about the hypoeutectoid steel. So can I go to this board over here? So hypoeutectoid, should I call it steel? Okay. So we discussed proeutectoid. So proeutectoid is the temperature thing, meaning above 727 degrees centigrade, what happens above the 727? Now hypoeutectoid means what's happening below 0.77% composition. What's happening at lower carbon concentration than the eutectic. So as we already mentioned over here, that the gamma austenite transforms into gamma plus delta. So there I drew the diagram where I drew some grains. So this grain I've drawn like this. Most of the grains are equal size. So these are grains of austenitite, and this is at a temperature, let's say 900 degrees centigrade, just as an example. So all these grains will look kind of circular and equal size. So these are called equiaxed. So equiaxed grains of austenite. So this is a very common term in metallurgy, equiaxed, meaning this grain, in whatever direction you look, it has the same dimension. So if this is the dimension in this plane, if I were to look perpendicular to the plane, it would have the same dimension. And all the grains have approximately equal size. So we're cooling down from the austenite, and at this temperature we'll get some alpha precipitating out. So in the previous diagram, I just drew a precipitate like this, right, of alpha. Ferrite, this is also called ferrite. I didn't mention ferrite so far. Okay, I'm sorry. So this alpha, the metallurgical term for this is ferrite. And of course, Fe3C is cementite. Okay, so this ferrite doesn't precipitate like this. It precipitates differently. It'll decide to precipitate on one side of the boundary, not the other side. So it'll keep growing in this side, and nothing will happen on the other side. So let's call this gamma. This is gamma 1 grain. This is gamma 2 grain. So this ferrite that is growing will have a certain orientation, right? So this orientation will have a link to gamma 1. So this ferrite is growing, it's almost like it's growing on gamma 1. It has a relationship with gamma 1 in terms of orientation, not with gamma 2. So this growth of ferrite, the way it grows into the gamma 2 will be related to the gamma 2, let's say, orientation. And we haven't discussed crystal structure as yet, but just think of a cubic crystal structure. This is, I've just drawn in 2 plane, but in 3 dimension, it's cubic. Then this ferrite could grow like this, along this direction, or it can go along this direction, etc. In other words, the ferrite growing into gamma 2 has a crystallographic orientation to gamma 2. In terms of direction it grows, but its actual orientation is in sync with gamma 1. So this is also called, it's a big word, Widman-Staten growth. So this could be platelets, or it could be needles of alpha ferrite. So this could be needles or platelets growing in that direction. So by the way, so this information I'm giving today, it wasn't there when I was a student. So these discoveries were made later after I graduated. Okay, so as I mentioned earlier, if you have any Fe3C within the grains, so the alpha can also precipitate on the Fe3C. And if it does that, it'll have a relationship with Fe3C in terms of orientation. So that's the hypoeutectoid steel. Hypo means below the eutectic in terms of composition. And proeutectoid means above the eutectic. So these are terms which can be a little misleading. So now let me mosey on down to this side. So I don't know if you know what the word mosey means. Mosey means to walk coolly, slowly to one side. I don't know if that's American English or not. No. Okay, so now we get to, So we talked about the hypo. Let's talk about the hypoeutectic or eutectoid. Did I say eutectic over there? Oh, eutectoid, yeah. So hypoeutectoid steel. So hypoeutectoid steel is not that common. Remember I said most steel is from 0.2 to 0.3% carbon, and eutectic is a 0.77. So most steel is hypoeutectoid, like 99.9%. So only if you have to deal with knives and springs, which are very hard, so we would deal with, or piano wire, which is very strong. So for those few examples, you would use hypoeutectoid steel. So again, just to remind you, we're cooling from melting point coming down, and we are in this austenite region. So all steel has to pass through this austenite region. So that's, if steel is at this, if alloy is here, is cast iron. So all steel has to pass through austenite region. So right now, if we're in the austenite region, let me again draw an equiax structure. It's easy to draw this like this. So this is austenite. And I would say this is homogeneous. It is just one phase. And let's say we are at 1,000 degrees centigrade. So let's say we are over here. So now I cool from there slowly. When I get to this point, I get precipitation of Fe3C. Fe3C will also precipitate only on one side, not the other side. It'll grow in one direction. And again, its orientation, crystal structure will line up with gamma 1 grain. This is gamma 1, this is gamma 2. It'll grow into gamma 2, but its orientation relationship will be with gamma 1. So that's how cementite grows. Now suppose you had a residue of cementite over here, because instead of coming down this way, you went up that way, then cementite can also grow this way. Now one problem with cementite growing is it can actually grow and consume all the grain boundaries. So now notice that you have complete coverage of all the grain boundaries with cementite. That is not a very good thing, because cementite is brittle. So you're making your structure kind of brittle by having this cementite precipitate out over all the grains. So cementite is like glass, Okay, time is running fast. Okay, so what I want to do, as I mentioned earlier, I want to concentrate on this eutectoid reaction. So a couple of more terms, and these are used often. So what is annealing? So annealing means different things in different branches of engineering. So in metallurgy, when it comes to annealing, we have a very specific meaning. Annealing means you heat to some high temperature for various metals, it can be different temperatures. For steel, you have to move into the gamma austenite region. So heat to gamma, actually gamma is austenite, so it's redundant. So heat to gamma austenite region. So that's where, so you get in this range, and then you furnace cool. Meaning you, at 5 o'clock, you have already heated the steel for 1 hour, let's say. So you've been at 1 hour in the gamma region. If your steel is 1 inch thick, and then you turn the furnace off and you go home. So next morning you come, you're done with your annealing. So in India, I talked to some engineers in this low-tech factory. So how do you anneal your steel? So they actually make a bonfire, and somehow they put the steel in the bonfire, and then they just go home. Next morning, the fire is gone, and they pull the steel out of the ashes, and it's been annealed. So annealing is heating to the austenite region and cooling slowly. So that's one. But then there's another term called normalizing. So normalizing is, again, heating to the austenite region, let's say for 1 hour, for 1 inch thick steel, and then cooling in air. So that's normalizing. So you cool much faster, and you get different structure, microstructure, if you're annealed and if you're normalized. So right now we're only dealing with very slow cooling. So there are whole chapters on what happens to steel when you cool the steel faster. So, but right now we are just dealing with very slow cooling. So let's talk about this eutectoid reaction when we cool very slowly. So there's an experiment you can do. So we're just trying to understand the eutectoid reaction. So what we'll do is, let me draw a much bigger diagram, phase diagram. I'll just draw the eutectoid part of it. So this is temperature, this is percent carbon, this is 0.77% carbon, this is 0.22, okay, and somewhere down here is 6.7%. This is alpha plus Fe3C. This is the austenite. This is gamma plus Fe3C. This is alpha plus gamma, and this is alpha. So this is our phase eutectoid. So what we do is we have a little setup where we take a salt. So how does the metallurgist, if you ask a metallurgist to heat the metal to this temperature, so let's say we have that composition, and this temperature is 727 degrees centigrade. You ask a metallurgist to heat the metal to 728 degrees centigrade. So how would he do that? So what a metallurgist does is he takes a pot of salt. So this is salt. He puts this in a furnace, and he heats the furnace to 728 degrees centigrade. So this is the furnace. And so he'll take the metal, tie a wire to it. He'll dip the metal, the steel, in this molten salt. So this is molten salt. So we heat it to 728, 1 degree above the eutectoid. So then what does it do? So we want to cool it to 1 degree below the eutectoid. We want to study this reaction. So he has a second furnace ready to go with a molten salt. You could use the same salt, and this is held at 726 degrees centigrade. So what he'll do is he'll transfer the salt, the steel from here to there. And he'll hold it there for some time. So this phase transformation happens. You go from gamma to alpha plus Fe3C, and then what he wants to do is to lock this structure, whatever the microstructure is, he wants to freeze it. So you transfer this steel to water. And if the water contains NaCl, that's even better. So you cool faster. So in the old days, when they made swords for the king, they wanted the sword to be very strong. So what they would do is they would take that steel, they would heat it up in the eutectic region, say 1,000 degrees centigrade is white hot. So I don't know if I should say this in this class. They would actually take a strong slave and they would pierce this 1,000 degrees centigrade piece of steel through his body, his stomach, and that steel would convert to martensite. So I'm getting ahead of myself, but you would quench the steel to make it hard. But anyway, we're not talking about that today. So I just want to freeze the structure at 727 by quenching in water. But so let's get back to, okay, so we are at this temperature, but we cannot analyze the steel at this temperature because it's too hot for us to handle, right? We can't keep it there. So we quench it fast, and hopefully at room temperature, we have retained the structure. So we can only examine the steel at room temperature. So let's examine the steel. So let's do that. Let me see how much time I have left. Okay, I have 5 minutes. So we'll examine the steel in 5 minutes. So first thing is, what do we have in the steel? We know we have alpha plus Fe3C, right? So the question is, how much alpha, how much Fe3C do we have? We know that from the phase rule that the amount of alpha, so the alpha by percent, weight percent, will be 6.7 minus 0.22 divided by 6.7 minus 0.77. So that's how much alpha you have. And Fe, so this is the lever rule. Fe3C will be 6.7 minus 0.22 over 6.7 minus
0.77 minus 0.22.
yeah, 0.77 minus 0.22. So what I'm doing over here is the amount of alpha is this amount divided by that amount. The amount of ferrite is this amount divided by that amount. So amount of ferrite will be 0.77 minus 0.22 divided by 6.7 minus 0.22. The amount of alpha will be 6.7 minus 0.77 divided by the whole thing. So it turns out the amount of alpha is 7 times more than the amount of Fe3C. So now, of course, they have different densities, but if the densities were the same, so we haven't discussed what this eutectoid looks like, eutectoid structure, but it basically has lamellae plates of Fe3C in a matrix of alpha. So these plates have thickness, and some plates will go like this. So this thickness, if you compare thickness of Fe3C and the thickness, okay, let me write it differently. So approximately 7 times the thickness of Fe3C is equal to thickness of alpha. So this matrix region in between is 7 times more than the thickness of the ferrite. So basically, when you transform the austenite, it transforms into a structure which looks like this, and this structure is called pearlite. I think I spelled it wrong. Is it P-E-A-R or P-E-R? So I could have spelled this wrong. So pearlite, I think it's P-E-R-L-I-T-E, right? Let me check the spelling of pearlite. I should know this because I've been only studying this for 50 years, so I should know how to spell. Oh, it's P-E-A-R-L-I-T-E. So it's pearlitic structure. So when austenite at this 0.77% composition goes from austenite to below the eutectoid temperature, you get a structure called pearlite, which is a lamellae of Fe3C in a matrix of alpha. Interestingly, all these alphas, even though they're separated, they have the same crystal orientation. And all the cementites, they're separate from each other, they have the same crystal orientation. Of course, this one is different. So you have different islands. So in this microstructure, what are the constituents? So this word constituent means something. Before that, let me just recap. What is a component? What are the components of the iron carbon diagram? So components are Fe and C. So those are two elements. So the elements in the alloy are called components. The constituents are when you look in a microscope, you see a dark region and a bright region. So a bright region is a constituent, the dark region is a constituent. Now, if you look at this pearlite, it has two, at very high magnification, it has two constituents. One is alpha, the ferrite, and one is cementite. So I think on that note, I'll stop. So we'll meet in 2 weeks, and we'll continue with steel and then we'll talk about cast iron a little bit. Thank you, guys. Have a nice week.